Apparent capacity versus actual capacity, subtractive volume. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already mastered. In our previous lessons, we focused on what we call additive volumes. This is the process where we take two or more separate solids and add their volumes together to find a new, larger total volume. However, as we move into more complex geometry, we need to prepare for different real-world scenarios. Often, we encounter situations where the interior space of a solid isn't just empty. Instead, a portion of that space is actually occupied by another object sitting inside it. When this happens, we can no longer simply add volumes together. Instead, we must use a method called subtractive volume to determine the remaining usable space. You will most frequently encounter this concept when we discuss capacity, which we will define in more detail in the next few slides. So, keep that idea of taking away or subtracting in mind as we proceed. Understanding capacity. Now that we've introduced the concept of subtractive volume, let's take a moment to really define what we mean when we talk about capacity. In mathematics, capacity refers to the specific amount of a substance, such as a liquid or a gas, that a container is able to hold. Now, you might be thinking, isn't the volume of the container the same thing as its capacity? Well, not quite. While we often use these terms interchangeably, the volume of a container only represents its capacity if the interior is completely empty and unobstructed. As we are about to see in the next few slides, if there is something taking up space inside that container, the capacity will be different from the total volume. Keep this distinction in mind as we move on to look at apparent capacity. Apparent capacity. Now that we understand the general concept of capacity, let's dive into our first specific term, apparent capacity. Think of apparent as what we see at first glance. Apparent capacity is the theoretical volume of the outer container, assuming the interior is entirely hollow and completely free of any obstructions or objects taking up space. Essentially, it is the volume we calculate based solely on the external dimensions of the interior space, as if nothing else were inside it. To make this concrete, let's look at an example. Imagine you have a standard cylindrical glass. We will define its internal radius as r and its height as h. Now, if the bottom of this glass were perfectly flat and there were no bumps or protrusions at the base, the apparent capacity would simply be the standard volume of a cylinder. Mathematically, we express this as apparent capacity equals pi times r squared times h. Actual capacity. Now that we have defined apparent capacity as the theoretical volume of a container if it were completely empty, let's move on to the more practical concept, actual capacity. Think of actual capacity as the real, usable volume available for a substance, like water or juice, to actually occupy. Now, here is the key difference to remember. In many real-world objects, the interior isn't perfectly smooth or empty. Sometimes, a container has what we call an internal protrusion. This is simply a part of the solid material that sticks up or pushes into the interior space. Because this protrusion is made of solid material, it takes up space that would otherwise be available for liquid, effectively reducing the total amount the container can hold. So, how do we calculate this mathematically? To find the actual capacity, we take the apparent capacity we discussed in the previous slide and subtract the volume of that internal protrusion. In mathematical terms, we express this as actual capacity equals apparent capacity minus the volume of the internal protrusion. In the next slide, I will show you a step-by-step process on how to approach these types of problems systematically. Step-by-step process for calculating actual capacity. First, your very first task is to identify the outer shape. Look closely at the main container. Is it a cylinder, a cuboid, or perhaps a prism? Once you've identified its geometry, calculate its volume. This value represents your apparent capacity. which, as we discussed in the previous slides, is the total volume as if the container were completely empty. Second, you need to identify the internal protrusion. This is the part that is taking up space inside the container. Determine the geometry of this object. For instance, it might be a hemisphere or a smaller cylinder, and calculate its volume separately. Third, once you have both volumes, it's time to perform the subtraction. To find the actual capacity, simply subtract the volume of that internal protrusion from the apparent capacity you calculated in step 1. This gives you the remaining usable space. Finally, and this is a crucial step to avoid errors, always verify your units. Before you even begin your calculations, ensure that all dimensions, like radius and height, are in the same units. And once you reach your final answer, make sure it is expressed in the correct cubic units, such as cubic centimeters or cubic meters. Following these 4 steps will ensure your calculations remain accurate and organized. Now that we understand the difference between apparent and actual capacity, let's walk through a clear, step-by-step strategy you can use to solve any problem of this type. Real-world example, the designer glass. Now that we have understood the theory behind apparent and actual capacity, let's put it all together with a practical application. Please look at the scenario presented here on slide 6. Imagine we have a designer glass. If we look at its basic shape, it is a cylinder with an internal radius of 7 centimeters and a height of 15 centimeters. However, there is a catch. The base isn't flat. There is a hemispherical protrusion pushing upwards into the glass, and this hemisphere has the same radius of 7 centimeters. Our goal is to calculate the actual capacity of this glass. Let's follow the step-by-step process we discussed in the previous slide. Step 1, we first need to find the apparent capacity. As we learned, this is the volume of the outer container as if it were completely empty. Since the outer shape is a cylinder, we use the formula. Pi r squared times h. Plugging in our values, we have pi, which we'll take as 22/7, times radius of 7 centimeters squared, times a height of 15 centimeters. When we calculate this, 22 divided by 7 times 49 times 15, it simplifies to 22 times 7 times 15, which gives us an apparent capacity of 2310 cubic centimeters. Step 2. Now, we must identify the volume of the internal protrusion that is taking up space. In this case, the protrusion is a hemisphere. The formula for the volume of a hemisphere is 2/3 pi r cubed. Using our radius of 7 centimeters, the calculation becomes 2/3 times 22 divided by 7 times 7 cubed. This simplifies to 2/3 times 22 times 49, which equals 2156 divided by 3. When we do the division, we get approximately 718.67 cubic centimeters. Step 3. Finally, we perform the subtraction to find the actual capacity. As we established in our formula, we subtract the volume of the protrusion from the apparent capacity. So, we take 2310 minus 718.67. This leaves us with a final actual capacity of 1,591.33 cubic centimeters. As you can see, by subtracting the space occupied by the hemisphere, we found the true amount of liquid the glass can hold. Keep this logic in mind, because in the next slide, I will highlight some common pitfalls to avoid when performing these types of calculations. Common mistakes to avoid. Now, before we wrap up today's lesson with our final summary, I want to pause and discuss some common pitfalls. As we've seen in our designer glass example, calculating subtractive volume can get tricky, and I've noticed a few recurring mistakes that you should be very careful to avoid. First, please be careful not to confuse surface area with volume. It is a very common error to see a protrusion, like the hemisphere we just calculated, and mistakenly try to subtract its surface area from the container's volume. Always remember, capacity is a measure of the three-dimensional space inside, which is volume, not the measurement of the outer skin or surface area. Second, pay close attention to your radius usage. In many problems, especially those involving a protrusion at the base of a cylinder, the radius of that protrusion might be the same as the container, but it doesn't have to be. always double-check the problem statement to see if the radius of the inner object is different from the radius of the outer container. Third, regarding your calculation order, I strongly advise you to calculate the individual volumes of the outer shape and the internal protrusions separately first, before you attempt to subtract them. While it might be tempting to try and combine everything into one long, complex equation to save time, this is where most algebraic errors happen. Keep it simple. Find volume A, find volume B, and then subtract. Finally, never ignore your units. It is easy to get caught up in the numbers, but a volume calculation is incomplete without its units. Always ensure your final answer is expressed in cubic units, such as centimeters cubed or meters cubed. Keep these points in mind, and you'll be well on your way to mastering subtractive volume. Now, let's look at our final slide to recap the key takeaways from today. Key takeaways. First, remember that apparent capacity is simply the total internal volume of a container, calculated as if the inside were completely empty and free of any obstructions. Second, we have actual capacity, which is the real, usable space left over after we have accounted for any internal obstructions or protrusions pushing into that space. Third, the core mathematical concept we've learned today is that the operation used to find this actual capacity is subtraction, which we refer to as subtractive volume. Finally, to keep it simple, you can always rely on this formula summary. Actual volume equals the volume of the outer solid minus the volume of the inner solid. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. If you can master this subtraction method, you'll be able to solve any complex capacity problem. Great job today!